Hello friends, my name is Abhijit and today I am going to talk about Theodolite, in which we are going to measure height of an object where the base is not accessible. So before moving on to the following topic, let's see what is meant by trigonometric leveling. So the definition of trigonometric leveling is as follows. Trigonometric leveling is the process of determining the difference of elevations from observed vertical angles and known distances. The vertical angles are measured by means of theodolite. So, for trigonometric leveling, there are two cases where the first one is the base of the object is accessible and the other one is the base of the object is not accessible. In this video, I am going to talk about where the base of the object is not accessible. So, there are following types in this method. The first one, A, when the instrument is shifted to the nearby place and the observations are taken from the same level of the line of sight. In such case, we have to take the two angular observations of the vertical angles. The instrument is shifted to a nearby place of known distances, and then with the known distances between these two and the angular observations from these two stations, we can find the vertical difference in distance between the line of sight of the instrument and the top of the object. So the second part is B, when the line of sight of the two instrument setting is different. Here again there are two cases. When the line of sights are at small vertical distance, which can be measured through the vertical staff readings, and the second one is when the difference is larger than the staff reading. In first case, it is advised to apply the formula for the difference in the height of the top of the object from these two lines of sight. The difference in lines of sight is same as the staff readings difference. When the staff is kept at a little distance from these 2 points, we can get the solution for the vertical distance easily. Second, in the second case, there is need to put a weighing staff at the first instrument, and the angle of elevation is measured from the point which is second from the observation. This gives us the difference in the line of the sights between the 2 points of the instrumental station. Then again we do the same. So the third type is when the instrument station and the object are not in the same vertical plane. In this case, there is need to measure at least two horizontal angles formed by the two instrument stations and the base of the object. Again, we will take the vertical angular observations from the two instrument stations also, and then we can apply the sine rule to solve the horizontal distances of the triangle with the help of these angles, and the distances we can get the vertical distance between any 2 points, that is instrument station and the top of the object. So let's look on to the methods of determining the elevation of point by theodolite in a deep manner. Here we are only going to study the last two cases, which is case 2 and case 3. The case 2, where base of the object is inaccessible and instrument stations in the vertical plane are as elevated object, and the case 3, where base of the object is inaccessible and instrument stations are not in the same vertical plane as elevated objects. So moving on to case 2, where base of the object is inaccessible and instrument station in the vertical plane as the elevated object. So there are two cases in case 2. The first one is where instrument axes are at the same level, and the second where the instrument axes are at the different levels. This one contains two more cases again. So the first one is height of the instrument axis never to be lower than object, and the second one is height of instrument axis to be higher than object. So in the first case of case 2, where instrument axes are at the same level, in the following figure you can see triangle PA dash P dash and triangle PB dash P dash. Here the triangles have angle alpha 1, alpha 2, and the height and the base is inaccessible. So moving on to triangle PA dash P dash, here H is equal to D tan alpha 1, and again moving on to the second triangle PP dash P dash, H is equal to B plus D tan alpha 2. So considering these two equations, we get D tan alpha 1 is equal to B plus D into tan alpha 2. Therefore the final outcome we get is D is equal to B tan alpha 2 divided by tan alpha 1 minus tan alpha 2. So H is equal to B tan alpha 2 into tan alpha 2 divided by tan alpha 1 minus tan alpha 2. Here RL of P is equal to RL of benchmark plus BS plus H. So moving on the second case where instrument axes are at different levels. So the first type here, when we see into this figure where the triangle PA dash P has H1 is equal to D tan alpha 1 and triangle PB dash P dash where H2 is equal to B plus D into tan alpha 2. Here HD is the difference between two heights. HD is equal to H1 minus H2. So HD is equal to D tan alpha 1 minus B plus D into tan alpha 2. Therefore the final outcome we get is D is equal to HD plus B tan alpha 2 divided by tan alpha 1 minus tan alpha 2. Again further, when we split this equation, we get D is equal to B plus HD cot alpha 2 into tan alpha 2 divided by tan alpha 1 minus tan alpha 2. As H1 is equal to D tan alpha 1, we get H1 is equal to B plus HD cot alpha 2 into tan alpha 1 into tan alpha 2 divided by tan alpha 1 minus tan alpha 2. So moving on to the next part where instrument axes are at different levels. Here height of instrument axis is greater than the object. So when we see this figure, there are two stations, station 1 and station 2. In station 1, the triangle PA dash P dash is formed. Here H1 is equal to D tan alpha 1, and moving on to the station 2 where the the triangle is P B dash P dash. Here H2 is equal to B plus D into tan alpha 2. Here again HD is difference between two height. Now HD is equal to H2 minus H1. So HD is equal to B plus D tan alpha 2 minus D tan alpha 1. Therefore, the final outcome we get is D is equal to B tan alpha 2 minus HD divided by tan alpha 1 minus tan alpha 2. This equation can also be written as D is equal to B minus HD cot alpha 2 into tan alpha 2 divided by tan alpha 1 minus tan alpha 2. As we know, H1 is equal to D tan alpha 1, so we can write as H1 is equal to B minus HD cot alpha 2 into tan alpha 1 minus tan alpha 2 divided by tan alpha 1 minus tan alpha 2. Now, when we see these two equations of D and H1, we get D is equal to B plus or minus HD cot alpha 2 into tan alpha 2 divided by tan alpha 1 minus tan alpha 2, and further H1 is equal to B plus minus HD cot alpha 2 into tan alpha 1 minus tan alpha 2 divided by tan alpha 1 minus tan alpha 2. We find these two equations similar, but the difference is in H1 we just multiply it with an extra tan alpha 1. Now moving on to the third case, where the base of the object is inaccessible and instrument stations are not in the same vertical plane as elevated object. Here in this figure we can see there are two stations, station A and station B. Here we set up instrument on A, measure alpha 1 to P, and angle BAC is equal to 0, as we can see in this figure. Now set up instrument on B, measure alpha 2 to P, and here we get angle ABC is equal to alpha. So angle ACB is equal to 180 degree minus 0 plus alpha. Now applying sine rule here, BC is equal to B into sine theta divided by sine of 180 degree minus 0 plus alpha. And for AC, by sine rule we get B sine alpha divided by sine of 180 minus theta plus alpha. So here we get H1 is equal to AC tan alpha 1 and H2 is equal to BC tan alpha 2. So we have learned how to measure the distance of the object or any building where the height and the base is not accessible to us. So with the help of theodolite we can measure the angle between those two triangles, and with the help of trigonometry we can solve these equations.